Hi, I'm going to show you how to use a technique called substitution to work through some pretty specifically engineered integration problems. And I call this the unchain rule. And that said, I suppose now is a good time to review the chain rule for differentiation. So recall that when we're trying to differentiate a composition of functions, right, where we have a function g that's embedded within f, what the chain rule says is to take the derivative of the outer function, which would be f, with the inner piece intact. And then here comes our chain step times, by the chain rule, the derivative of that inside piece, the derivative of g. Alright, so that said, if let's suppose I were to take the derivative of sine of 5x, right, where now my inner function is that green piece, right? And what the chain rule says is differentiate the outer piece first. So the derivative of sine is cosine, and keep that inner piece intact, and then differentiate the outer piece. So, differentiate the inner piece. So the derivative of that 5x is 5. So the derivative of sine of 5x is 5 cosine 5x. Rewriting, just taking that 5 and put it out front. Okay. Now that said, there ought to be a rule for integration that's similar to that, or accounts for that chain rule with integration. Of course, integration and differentiation are very much related, kind of opposite processes. So let's take a look at some examples where we might use this. Let's give you an example first where we don't need to use the substitution. Okay. For this particular antiderivative indefinite integral, I'm just going to use a power rule. So we bump the power up one and divide by the new power. Right? Throw on a plus c, or constant of integration, at the end. Right? And to check, that's going to work out nicely. So here's my check. So I'm going to take the derivative of what I think is the antiderivative, and we're going to bring the 4 down, so it becomes 4x cubed over 4 plus c. The derivative of plus c is 0, and of course we get x cubed, which is what we want. Okay, so that works out just fine. Let's look at an example where it's similar, but one way to think about this problem would be to use a technique called substitution. So, kind of working off antiderivative x cubed, one way to do the antiderivative of 2x minus 1 cubed would be just to multiply it all out and go term by term, which is nothing wrong with that. But notice how we have, in this case, a function embedded within another. And this technique doesn't always work, but here's what I'm going to do. I'm going to use a clever little substitution, and I'm going to let u be my inner function, 2x minus 1. Okay? Now, if u is 2x minus 1, then the derivative of u with respect to x is just going to be 2. Right? So I'm taking the derivative of 2x minus 1, which is my u, and let me make it look like a u, not a v. And the derivative of that u is 2. Okay. Algebraically, what I can do is I can multiply both sides by dx, and I'm just going to move that dx to the other side. Okay. That du, we'll talk about what that means later. Okay. It's called the differential. What I can do now, however, is substitute. So if u is 2x minus 1, then that becomes u cubed. Right? And I'm left with a dx. Right? And dx is, well, if I solve for dx here, I get half of du. Okay, so another way of saying du is 2 dx is if I divide both sides by 2. Okay, another way to rewrite that would be du over 2. So I can take that here and plug the 1/2 here and the du here. And what I've done now through the substitution is I've rewritten a little bit more complicated integrand with an x and a dx in terms of u and a du. Okay, and that's what this process of substitution allows us to do, to take a kind of messy, or much messier later, integrand, which we're trying to integrate, and replace it with x's and a dx in a much nicer form with a u and a du in it. Okay, and now I'm going to go ahead and integrate that just as I always would. That 1/2 comes along for the ride, it's a coefficient, And I'm going to use a power rule to integrate u to the fourth. U cubed, which is going to be u to the fourth over 4, right? And so what that ends up being is 1/8 u to the fourth when I multiply 1/2 by 1/4. And now I'm just going to take my original u and plug it back in. So it's 1/8 times a quantity, 2x minus 1 to the fourth plus that constant of integration. Okay, and that is a correct solution. And let's make sure it's a correct solution. So let's differentiate that just to make sure. And so here's my check. Oops. Sorry. Oops. There we go. So here's my check step. I want to differentiate what I think is my antiderivative, see if I get 2x minus 1 quantity cubed. So I'm going to differentiate this guy 1/8 times a quantity 2x minus 1 to the fourth. To do so, I'm going to use a chain rule. So here's my inner function. I'm going to put it, bam. That 1/8 comes along for the ride, times, I bring the 4 down, times a quantity inner function to the third using the power rule, times now by the chain rule the derivative of that 2x minus 1, which is 2. And what happens is the 1/8 times 4 times this 2 clears. That all becomes 1, leaving me with what I want, 2x minus 1 quantity cubed. Okay, so we're taking an integrand with an x and a dx in it and putting it into a more manageable form with a u and a du through this particular u substitution. Okay, let me show you another one, and this one we'll get our trig on. How about that? And so let's work with this guy here. Let's integrate x times cosine of the quantity x squared dx. Now remember, there's no product, well there's a product rule, but we don't integrate piece times the integral of another piece, right? That's not how derivatives work, so why would that be why antiderivatives work? Well, it's certainly not. So what we can do though in this particular problem is notice how there's an x squared here, and there's not exactly its derivative, which would be 2x, but a multiple of its derivative. So watch what happens in this particular problem. I'm going to let u be my x squared. Okay, and again, my goal is to take this messy integrand with x's and a dx in it and put it into a much nicer, more manageable form with a u, or maybe a couple u's and a du. And if I let u be x squared in this case, watch what du, the derivative of u with respect to x, becomes 2x. Right? Which I can then manipulate if I just take this dx, multiply both sides by dx. I get something that's helpful, and here's why it's helpful. Okay, here I have an x dx, and du is 2x dx. So what that means is I can replace a 1x dx with half of du, right? Because du is twice x dx. So what I have here is 1x dx. So this ends up being half of du, and I'm going to put the 1/2 here and I'll put the du over there just because it looks nicer. Okay. What the cosine of x squared becomes is cosine of my x squared, which was u. Okay, so cosine of x squared becomes cosine of u, which u was x squared. And since u was x squared, my du was 2 of these guys. Right? So what I have therefore is only half of what du really is. Okay, and now I've accomplished my task. I got a lot of x's and a dx, and just in this case 1 du and a u. So now I'm able to integrate, now that I've substituted to a much nicer version, and the antiderivative of 1/2 cosine is 1/2 sine of u, because remember the derivative of sine of u is cosine. And now all I'm left to do is to resubstitute my u and throw in my plus c at the end. Okay, and that looks like the right answer. Let's double check just to be sure. So let's check. Here's my check step. I'm going to differentiate 1/2 sine of the quantity x squared. The 1/2 is a coefficient, comes along for the ride. The derivative of sine of x squared, I have to use a chain rule. Remember, this substitution process is kind of like the unchain rule. So I'm going to differentiate the sine first to get cosine, leave the x squared intact, times the derivative of that inner times the derivative of 2x squared, which is 2x. right? And the 2 1/2 cancel, and we're left with cosine of x squared times x, which I'll just put that x out front. Great, that's what I want. X times cosine of x squared. Thanks for listening. That's substitution. We're going to do some practice problems to get used to this technique and how it helps. But in general, we want to turn a fairly messy integration problem into a little bit easier, and we do that through the substitution with u's and du's and dx's and whatnot. Thanks for listening. We'll work through this tomorrow in class.